Hello, I'm Mike McCulloch. Today I'd like to talk to you about the cosmic microwave background, which is a radiation that comes from all parts of the sky and was discovered in 1964 by Penzias and Wilson. And it's a radiation that looks like it has a temperature of about 2.7 Kelvin. And many satellites have been launched to look at it in more detail, like Kobe, WMAP and Planck in 2013. But as well as the general temperature coming from all directions, there are variations, very small variations, about 1 in 100,000 of the temperature when you look at it in different parts of the sky. And there are many patterns within the CMB, but what has been noticed, and which is very interesting, is that when you look at it on the larger scales, it seems far too smooth. So they tend to define scale using a multipole, which is determined by L, denoted L. And they said that the multiple of L equals 1 is the full width of the sky, so these are on the largest scales, whereas when you go to higher multiples, these are smaller angles on the sky. So a multiple of L equals 40 would be 180 all across the sky divided by 40. And they found that if they look at this data for multiples of less than 40 and average them, then the intensity of the radiation is about 5 to 10% less than it should be, according to lambda CDM, the standard model of cosmology. So this is interesting because quantized inertia predicts something very similar. As you know, quantized inertia, the basic idea is that waves that do not fit within the cosmos cannot exist. And as waves get longer, unreal waves or any kind of wave or any pattern, as these patterns get larger, fewer of them are going to be able to fit. So you can quantify this using the equation shown here. So the intensity in the spectrum of the radiation should look like something like this. E prime, so that's the modified intensity or energy, is going to be the original one times a factor of 1 minus lambda m over 4 theta. And as I alluded to earlier, L is 2 theta over lambda m, so 2 theta is the width of the sky. It's actually twice it, but that's a detail. And lambda m is the wavelength we're talking about. And this means that the modified energy is equal to E times a factor 1 minus 1 over 2L, where L is the multipole. And if you do the calculations here, and they're shown in this plot, then you get a suppression of patterns on the larger scales. So this plot shows the multiple along the x-axis from L is 1 to L is 40 on the right, and the intensity of the radiation up the y-axis. And you can see that the observations are the black line, and you can see there's a bit of variation, but also on the far left, the intensity drops very rapidly for the highest multipoles. Now, lambda CDM is shown by the dotted line, and you can see that especially on the far left, it overestimates the intensity quite dramatically. And then when you apply quantized inertia, you get the dashed line, which is far more in line with the data. So, as I said, if you take the energy in the top 40, well, the bottom 40, L is 1 to L is 40 multiples, you get a reduction in the observations of about 5 to 10%. QI predicts 5.5, so that is consistent with the data. What quantized inertia also suggests is that you should have peaks in the cosmic microwave background, because at some wavelengths, these wavelengths will fit within the cosmic cavity, if you like, and at other wavelengths, they won't fit at all. And it should be possible to predict these peaks using a proper cavity model, which would be interesting to do. Okay, so I hope you've enjoyed this short. I published this in my first book, Physics from the Edge, and also in a paper in 2014. So you could have a look at those. Okay, so I look forward to seeing you next time. Goodbye.